Hello and welcome to IEEE Soft Robotics Podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa Edwini, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
So I would like to ask you first how you would like to define yourself for the audience maybe first time listening to you.
Yeah, I am biologist as background, actually marine biologist. And I started my research in the field of biophysics, studying the impact of pollutants like mercury and heavy metals on the environment and the human health. And then I moved to engineering, to the engineering side. I have a PhD on microsystem engineering. And then I started work first with the microsystems, in particular microfabricated sensors, again for the environment, air quality. And then I moved to the service robotics, in particular again for water detection and air detection. And finally, I start to work in the field of biosphere soft robotics. And so I try to merge biology and the engineering.
Great. So first of all, I'm curious to ask you the transition from biology to engineering. I don't know what's challenging for you, this decision to do it after being established in biology field. I'm curious about this transition, the decision to do that.
It was quite difficult in the beginning, you can imagine, especially the scientific approach, the method are quite different, and also the terminology. So the first point was try to understand each other with my colleagues. When I started, I was together with engineers mainly. And so the first challenge was try to really investigate the problem from an engineering point of view and try to better understand the problems from that perspective. So this was really the challenge. And the idea was, as I said, I was this training in biology and biophysics. And then I did an international master on environmental management at the Scuola Superiore Sant'Anna. And this was the way in which I entered in contact with Professor Paolo Dario at that time, that looked for biologists to collaborate and try to develop technologies for environment. And so I started to work in this field. And after understanding how to approach the field, I can say that it's really exciting and motivating for me, because you can see the problem from different perspectives, and this is very interesting. So you can really understand and use your background to better understand the problem from also an engineering point of view. And this was great. But I have to say that the beginning was quite difficult. In fact, it was not simple.
Yeah, it's interesting. But I'm curious to ask you, what could be in that experiences you have the biggest question or hard problem? You still don't know how to answer them. Maybe from biology, since you're merging both of them, but still hard to find an answer or even understand them.
Of course, as I say, that it's not easy to merge these two, not only biology and engineering, but different disciplines together, because fundamental to try to understand each other. So the language that we use, in the scientific language, is fundamental, the terminology, having really an open mind, and to be contaminated from the other fields, from the other discipline. Another challenge that I had to face, at least 10 years ago, more or less, was when I proposed, in fact, to the community plants as a model. This was another challenge, because these organisms, in fact, are often not considered as a model for technology, you know, because our perception of this living organism is usually that they are quite static. There are no capability to interact with the environment or to communicate. So the question at that time was why you want to take inspiration from plants to develop robots. So what is the reason? Yeah. And especially I start with soil, I mean, the problem of soil exploration. And so the point was there are many animals that can do that. Why you want to propose plants? But now I have to say that there are many groups that work on that. And so they start to consider plants as a model, and especially in the concept of growing capability. So we can really open new field, now take inspiration from this model. And so something's changing, actually. Also in the perception in general of biology and emerging biology into artificial field. So the approach is completely different with respect to 10 years ago.
Yeah. But I'm curious to go in the starting point to propose the idea of using plant, because you said that people think that's crazy. Why you choose that inspiration? And that leads me a question: when we design soft robots, for example, and try to get this inspiration from the nature, what are the elements you look for? What kind of question you ask? For example, when you start to think about plant, what kind of question lead you? That's had the potential here, and that prove people that's right.
Yeah, there are many now questions that we are trying to, and problem that we are trying to solve, take inspiration from plants. But the original question was how we can monitor soil by developing robots that move autonomously in this medium that is very complex. So it's very heterogeneous. There are high pressure, high friction, and very few centimeters of the soil. And so this was really one point in which I try to merge my competence in biology together with engineering, because I say that, look, the living organism that is better adapted to this extreme environment is the plant, because they can create with their roots, they can create a network, they can penetrate in a very capillary way the soil. They have a behavior because they can grow following or escaping from environmental stimuli. They can communicate. This is also very interesting from an artificial point of view, because they create a network with other plants, also mediated by fungi and other organisms. So they create a sort of wood wide web. They create a complex network in soil to be much more effective and efficient in soil exploration. So the point is more from a technological point of view, how we can translate all this idea, this performance in an artificial system, but no doubts that they are the best organism adapted to this environment. And so the point was starting from the observation, and this is another challenge since they move in soil. So how we can observe the dynamics of the movement, so the strategy that they adapt to move in soil, since they move in soil, under soil. So there are very few techniques that we can use to observe the dynamics of the movement. But this is exactly what we need to translate then this feature into control or artifact that are able to grow, to move in soil. And so what we start is actually by developing setup for the observation of the root movement. The observation is fundamental, is the first step of the scientific method. So we need to observe the movement, the strategy of living organism to understand how they adapt to a specific environment. And so we developed this setup also using time-lapse video, so we can record the video, then we accelerate the movement, We can use a different soil, of course. There are mainly artifacts, especially phytogel or transparent soil in order to observe, and is a simplification. We know that is a simplification, but we need for, observing the dynamics of the movement. And then was a long process also to understand the main important features and the secret in the movement of the root in soil. Because initially we imitated some function, the roots, but they were not the real secret. That is, in fact, the growing. So they move by growing, not only in soil, but also in the upper part, in the shoot. So they add the new cells by cell division in the root, so in the apical part of the root. And then, and this is very important as well, they absorb water from the environment. And so it's a sort of hydraulic system, and they push the tip into the soil. And they also adapt the morphology to the external environment. So they can change the diameter, they can produce a hertz for anchoring soil. So there are many features that are fundamental for the natural organism, and then now we are trying to imitate in our artificial system. But understanding that these are the main point, the main features that we need to translate require time and a lot of experiment, a lot of hypotheses, a lot of prototypes that didn't work also. And so we learn by doing, because sometimes you don't have a data from a biological point of view that you can immediately translate into specification in the artifact. And now there are many other points that we are starting to consider from the plants.
That's very interesting. Maybe the first question I would like to ask you, what does it take so that you can answer the secret, how they actually work? And you mentioned also sometimes, I think it related to embodied intelligence, whether should it be the brain or the body or beyond both of them. And you mentioned the exhibit intelligence example for the throated bodies. So how that work when you try to understand how they can adapt their morphology? What does it take to answer how it's happened, or the missing pieces here to understand how it happened?
Of course, again, they are a very great example because they don't have a brain at all, but they have we can call a sort of distributed control that are mainly in the apexes, not only in the root but also in the shoot, as I said. And this is very interesting because they perceive the environment, but they have many apexes that perceive several targets, several stimuli at the same time. So it's quite complex to take a decision without a brain. So because this is actually, and so we can understand, it's a sort of platform for us to understand how we can design our robot in which the body has an important role, interacting with the external condition, reply to certain stimuli, implementing also some smart behavior, for example, based on priority or phenotyping, how this priority changes on the basis of the external condition, the basis of the internal needs. And so, since in this model there are no brain at all, we are forced to consider the role of the body, the sensing, the interaction with the environment, and without considering a central unit that take a decision at a higher level. Because in this case, it's a more distributed control and internal communication, the external communication to optimize the strategy to survive, because this is the goal of all the living organisms when they have to adapt to any environment, especially extreme environment. So for us, it's a perfect platform to improve our learning strategies, so how we can develop software robots that also exploit the environment to reduce the complexity of the control. This is another big challenge. And again, now with a recent project, we are using, for example, plant seed exactly to, as a model to develop software robots that move into the environment without any control. But the control is embedded in the arrangement of the materials and their capability to interact with external conditions, especially humidity, temperature, but also wind and other external conditions. And so we are, for example, imitating the drilling capability of seed or the flying capability of seed that are only given by the materials, the structural material and other material that absorb and dissolve the water. And this absorption and desorption work from an artificial point of view as a sensing and as an actuator at the same time. So we can implement a multifunctional capability in our robots, again, take inspiration from this model. And this is an extreme, if you want, the concept of morphological computation. There are many examples, not only in plants, of course, but plants for me is really, as I said, a platform of study to investigate a completely different behavior since they don't have a brain. So I cannot use in my robot a centralized control since I take inspiration from plants. So as I said, I'm forced to find another solution and to use the environment in the design of this robot.
Yeah, that's very inspiring. But you mentioned many interesting points. The first one about using that kind of less control and make the body do most of the work. How do you see this point? Because I think that's something also in the community and even in rigid robotics, how we can exploit this kind of physics and also the nature dynamics of the material and less control. How you manage to balance both of them, the control and morphology?
I think that there are many, of course, many approaches. There are not just one. May I say that I'm very inspired by the natural organism in the sense that I try to see how they can do that. And we all, as a living organism, we use the environment in our movement, in our interaction, because this means really reducing the complexity of the control. There are some, also in robotics, of course, some model like the octopus that is another example in which we can see the importance of the exploitation of the environment for reducing the control. But also, again, we can see that this animal has a lot of neurons, the most of the neurons in the arms, not in the brain. Again, because probably there are no evidence in biology, but probably this is the reason, since the body is really complex, because there are infinite degree of freedom, there are no rigid skeleton in the body, so they can bend in any direction. They have the suckers, they can control each sucker, so they use it as a sort of fingers. So probably such a morphology needs more than one brain, need a lot of control distributed in the body, and also needs the body that interacts with the environment to help in the control. This is much more evident in plants because the morphology is still more complex. There are millions or apexes also in a very simple plant. And in this case, there is no brain at all. So as I said, it's very important to see how they can exploit the environment, like, as I said, the humidity, the temperature, the interaction with the other organism. So in the case of the plant, if you consider the forest, there is an emergent intelligence also given by this network that they establish not only internally to the same plant, but with other plants, with other organisms. So the flux of the information is shared with other organisms. So really from this extreme example example, because this is the case, so we can take a completely new idea. At the end, there is a sort of philosophy, that it's not only robotics, but it's also some advice in looking at nature to develop a new robot, but also try to take the lesson from them to be more effective in design this artificial system. It's quite complex because there is no, as I said, a unique approach. There is not a book that you can read not to understand how to translate nature in artifact and technology, but you can learn by doing, by also exploiting different approaches, by experimental trials that are fundamental from my side to extract the data from nature, to quantify some phenomena. And this is also the difference from a biological approach and an engineering approach. So in engineering, we need to quantify the phenomena, extract the numbers that then are translated into specification. So from this collaboration of these two different world, different disciplines, we can really learn each other. Because also in biology, we can really understand some phenomena in the biological systems by using the robots, by using this bioengineering approach. So it's really a continuous learning from both the sides.
Yeah, that's very interesting. But I think the question, when the community asks how we can use living material like planet with artificial one, and the question is how they can really continuously learning and adapt to the design, because in soft robotics sometimes we speak about how we can design the sensing capabilities, assuming we have passive material, no, smart material. And it's quite there's a trade-off between how you embed the sensing in the material and make sure it's stable as well. At the same side, we have the planet. They figured out how to do that in a nice way and should sense and have the body as well.
Absolutely. This is another important point that I think soft robotics is addressing, can address, because there is a quite a different approach with respect to the traditional robotics. So many groups that work in soft robotics are really inspired by natural organisms. So, and this means also generating new materials that embed sensing functionality. This is one of the challenges of our community. Now, all of us try to integrate different sensing properties, in particular tactile properties, but not only, how we can perceive the external environment, also proprioception, by developing such kind of material. And in fact, is fundamental the collaboration with the expert of materials, because in many cases they already solve our problems. So they already develop, for example, material with sensing property embedded in the structure, but also materials that are, for example, biodegradable or reusable. This is another point that our community has to address in the future, developing technology that is much more sustainable. And this means also that our materials, but also the electronics, the energy, should be more integrated into natural ecosystems. Because many of us have as a target, in terms of application, the exploration of the environment, or agriculture, or environmental monitoring. So this means that we need to develop technology that at the end are fully integrated in natural ecosystem. But this, again, this means that we have to reduce the impact, the negative impact of technology into natural system. And so the key point is developing material with more functionality. And so also in my group, we are trying to work in this direction, but there are many groups that work on this. So how we can develop a continuum, for example, structure, or growing structure. This is our challenge. So how I can develop a continuum structure that also embeds sensing properties. This is one of the challenges that we are facing. But at the same time, this structure that maybe I used for detecting parameter in soil or in air or in different conditions cannot then at a certain point be released in the environment and contaminate the environment, because this is not more the way in which we have to develop technology. So we need to consider the final, so the cycle or our technology starting from the design phase, no more at the end, because otherwise, the risk is to continue to release technology in the environment and create contamination. So there are many aspects. So this is increased the complexity, because there are many functionality that you have to consider. So sensing is the first, but then structural properties is not only the sensing, but maybe you have to consider material that give also the structural functionality to the robot, and then the capability to interact with external conditions, reduce the impact. So there are many points that we have to consider in the design phase.
That's really important point, and I would like to thank you for mentioning that. But I think coming back to the design, because I think that's why we design what we design. And you mentioned that this obligation that we make sure at the end of the day what we develop is safe or biodegradable. And it made a lot of complexity, because in research sometimes we tend that to publish as the result as it comes, and we don't consider that consequences are behind what we do. And it happens sometimes, and there's a pressure to, it works, it's okay, let's get it published, but it takes a lot of time to figure out this question, and it takes time, apparently. So how do you see this kind of changing? Because I think that's something need to change it, though. And you have a lot of expertise in that. So what are your thoughts about that? What kind of things do you think we have to address in the design process to make sure we're going at least in the right direction overall?
Yes, you touch a very important point, because of course we have to publish. So there are many pressure in our work. But I think that in design, during the design of our robot are fundamental, is a crucial part of our work. And so in addition to the point that I have already mentioned, this means that we have to consider also the energy aspect during the design. And this is of course obvious, but it's not so obvious when then we develop our system. So taking in consideration the energy needed for operating, especially in real field, of course, this is the point, in extreme conditions. So, and again, I think that if we are able to really see the crucial point from a natural organism, again, they can help on this. Not because the living organisms are perfect or they don't have a problem in terms of energy, because they have, of course, but they need to save energy in certain point, because otherwise they die. And so also at the design level, we can really understand and try to identify what is needed also from an artificial point of view. This process is really complex because, as I said, at least for me, when I identify the model, the living model that I want to imitate to try to address a specific problem, then the next step is really to understand what are the features that are relevant to solve my problem. And it's not so evident, because in a natural organism, there are many functionalities that are not relevant for us in the artificial world. But they need for the replication, for the surviving in a certain environment, for eating, for the reproduction, and so there are many aspects that are relevant for a natural organism that probably are not relevant for us, for the artificial counterpart. But looking at the strategy implemented to save energy is another point that we can try to integrate in our design. And this is very, very complex from my point of view. I try to do with our with my group, especially in these recent projects that we have, as I say, the not only plants, we also have soft animals that we are investigating. So how these organisms save energy, interacting and doing something in the environment, and doing something in their habitat. So this is the crucial point. But I think that this is another point that we need to consider: energy. Energy is crucial for developing robots, autonomous robots for real environment. And materials, again, can help a lot, because if we increase the functionality, the performance of the material, we can probably reduce a part of the energy needed for operating in a real environment. It's not only material, of course, but it's an important part of the process.
That's very excellent, yeah. But going back to soft robotics, and we speak about how we can design them robust and reliable, and also for uncertainties. And I'm curious about when it happened to in the planet, like damage or failure. I don't know how they adapt to that. So from perspective of a design, how we can, I don't know, can we design soft robot that more robust, like a plant, how they can resist this uncertainty like damage or anything? Do you have any explanation for that?
There are some groups, as you know, that work in this. Again, as a material, we are not really addressing this point, but I think that is one of the crucial points for the future. For example, implementing, again, in the material, that means also material integrate in a robot, the self-healing properties, for example, because this is an important characteristic that some groups in soft robotics start to consider. And I think that these properties will change the way in which we also develop our robot, because at the end, they will be more robust. Of course, the process is not so short, because we need to understand how then to integrate the material and use this material inside, in a robot, not only as building blocks that are or in a laboratory condition in which you can recreate the structure by using temperature or other stimuli, even if there are a lot of progress in this sense. So many groups now use ambient temperature that is fundamental to be more close to the real application. So there are a lot of advances in this field. But then we need to move to the robot, and this feature probably will be one of the most important features in the future to be more robust in a extreme environment. The other feature that we could consider for our robot, of course, and not for all of them, but is to be redundant. This is another feature that we are investigating again in plant, since they really they can colonize any environment, also very extreme environment. They can be attacked by enemy or by also herbivorous animals and so on, because they are redundant. And this means to be very robust for also extreme environment. So in some cases, probably we could also consider this redundancy also in our robot. For example, also for the control or for the body or for other characteristics of the robot, because the redundancy means that even if a part is damaged, the system continues to work. So there are some feature that maybe in the future could be relevant also for us.
Yeah, that's very interesting about the redundancy. And yeah, I can't agree more with that. But yeah, that's very true. But I'm curious if there is something was counterintuitive, maybe through your research in the plant. So when you try to understand them, or you expect there's a behavior in a certain way, but it was counterintuitive or surprising. You didn't expect this behavior when you try to, yeah.
This is one of the big challenge that we have, and also understand them, as I said, because it's very difficult to observe. Some movements in plants are too fast, so you have to decelerate. and other are too slow, and many of them are too slow, so you have to accelerate, or they grow, as I said, in soil, so it's not possible to see directly the movement since they are slow, but also because they are in a medium that are very complex. So there are many challenges in not only in translating such a function in robots, but also in first really understand the living organism. And I really like this challenge because I really like I am biologist, of course. So for me, it's also important to understand how the living organisms work. It's a part of my research. And my dream, if you want, and my challenge in the future is more and more use robots for this goal. I think that we could open in the future new market that is dedicated to that. So the robots that become tools for scientists as a microscope. So robot in the future, more and more robot plus AI, because you can also increase the complexity in the behavior of our robot, also merging strategies that come from the artificial intelligence. And so you could use this as a tool more and more. There are some examples, but already in our field. So there are some groups that also we try to do that. So there are some groups, experts that try to use robots, also simple robots, to test some hypotheses in the biological field. But probably in the future, this probably become a new market. So not only specific application that for sure we can open, because soft robotics can open. It's still in an early stage, probably. There are many problems that we need to address, but already now we see the potentiality of this community, since we can open new scenario that now are not addressable from the other robotics that works very well. So that what we call traditional robotics already change our life, the way in which we develop our machines, our many stuff, our society are developed by industrial robots, or we can explore the space of deep sea by using robots. So that they are already very important tools in our hands. But in the future, with soft robots, we can really open new scenario in a medical field, in the exploration, in industrial context, because we could use the robot for extreme condition also in industry. There are many situations in which rigid robot cannot operate because the environment is really unstructured, also in industrial context. So there are many opportunities. Of course, we need to create more and more also industry companies that work in this field. But I think that another possibility is to use it for science. Use software robots, bio-inspired robots for science, and close the loop, if you want, back to biology. This is one of the one of the opportunity that we have, involving more and more scientists in the field. I think that they are more and more attracted by our community. I think so.
Great, yeah. But I'm curious about the growing aspect, because I think that the community, how you think this kind of growing capabilities could be more challenging if we speak about the future integrated living material with the robot and they can grow. What aspects could be challenging here?
There are many, of course, in the growing, there are many, because you have to create a body, a structure, starting only from, in our case, from an artificial tip, and then you have to deposit material to create the body. And so there are many, many functionality that you have to implement, as I said, the functionality in the material, the adaptation capability of the robot on the basis of the external condition. But for the moment, we are just using artificial structure, artificial material. The idea is to develop a biohybrid system in which you use living tissue is another hypothesis. Of course, the problem here is how we can interact with the bio part. So what I mean is, of course, a root, a plant works much better than my robot, no doubts about that. But the way is how can I communicate with the plant also to understand what the plant perceives in the environment, or also guide the plant in one direction or another direction. Of course, I can do this with a robot, and so the application is much more clear. It's much more challenging with a living system. So the developing also interface to communicate, to understand is not only a communication, is understand and that we are trying to do that with soft electrodes. So we are moving also in this direction, especially monitoring the electrical signal inside the plants. They use also this kind of communication, especially because they are fast communication with respect to the chemical signal, like in our cases. And so interpretation of the information that they collect, this is also another crucial point, in addition to maintain alive the tissues, because this is also very important, especially when you have to develop this biohybrid system for moving soil, for example, in which maintaining the structure, the interaction with also the artificial part, or only using the living system, but this means that you need to communicate in some way with the plants. And this is really, at least for me, it's really something very far. And so for the moment, unfortunately, I have to develop the robot because there is no alternative for now.
Mm-hmm. That's interesting. So since we close the end, I have a few questions. Maybe the first thing I would like to ask you, what kind of the trade-off you still have, and you can't really get rid of that? Because sometimes in the community we speak about that trade-off and design the material with kind of mechanical performance and response time. Of course, it depends what kind of material, what kind of the project you have, but what kind of trade-off in terms of the Plantoid project was kind of you can't get rid of, or you can't figure out how you can close this trade-off?
Yeah, I mean, there are many, in the sense that for the moment, the main point that we try to obtain is this growing, as I said, so, but there are other simplification that we know that are simplification, like the fact that the robot now is not, for example, able to use the environment, exploit the external condition to be more effective in the penetration. So we know that we need this behavior, and we are working on that. But the first point is how we can obtain such functionality. So for the moment, we pushing more on the growing by adding new material. But we know that at a certain point we have to exploit the environment, especially water in soil, for example, to be more effective, because this is exactly, so it's a material, first of all, because the material are fundamental also in my robot. So means that have structural properties, because you have to create a structure. They can interact with external condition, especially in terms of humidity variation. At the same point, they have to perceive the external environment. So these are the main functionality, and so we try not to move following this the direction in our. And so there are many compromise and many trade-off that we have to face along this path. Because so we are trying to develop some prototypes, and then we know that we have to go beyond following these specification, we can say.
Yeah, And I'm curious, when you try to think about pushing the capabilities of what you try to inspire from, like the plant, when you try to think with yourself, what I can do that beyond what we see in nature, because it's adaptable, design adaptable way. What kind of thoughts you have as like crazy ideas?
I mean, there are many here in this plan of crazy idea, I have to say. But one of the crazy idea, for sure, as I said, is to create the body with external soil or material that we have. So this is one of the crazy idea that we are trying to push in. And again, there are many organisms that do that, especially in soil, and but not only in soil, also in marine environment. So try to use the external environment to create a body or part of the body. It's a crazy idea, but I mean, natural organisms can do that, so we can see how we can, if we can imitate them in doing such crazy stuff.
Yeah. So question left. The first one, I don't know if you have moment of doubt. How you deal with doubt? Do you have doubt when you do research? How you deal with that?
Of course, many doubts, many. Many also when, especially when I say, when I propose this idea, when you have especially trained young people, and you propose this strange stuff, especially now I'm more confident because there are many groups in the world that study biology, or they push away in the direction of soft robotics, bio-inspired soft robotics. So now I say, oh my God, probably now it's not so wrong. But when I start, I had many doubts, because when you have a young group, with the young people, and they have to trust you, so you are proposing something completely out of the box, and is very strange. And so you say, oh my God, they have to discuss a thesis. They have to do the PhD, in these topics. So maybe are completely wrong, and there are no story in this direction. And so, especially when I have a lot of doubts when my ideas involve other people, because I share the risk with them, and so it's a responsibility. And then, of course, there is many doubts because sometimes say, oh my God, maybe this is wrong. I'm saying something that is not completely clear or demonstrate. So, I think the doubts are fundamental in our work, because it means that you refine the idea in some way. So to be completely sure about the statement about what we propose, I don't know if completely positive, in the sense, of course, you have to start from something, but having doubts means that you try to revise also your opinion, and to maybe better refine the approach or something like that. But as I said, my doubts are in particular when, especially in the past, of course, also now, but especially in the past and the beginning, when I proposed the first time, such a kind of idea, and the people look at me in a strange way and say, oh my God, what I have to do. And yes, but I think in a certain point, having doubts is fundamental in life in general.
Thank you for sharing that. Yeah. Lastly, I don't know what good kind of advice you received and was a life changing, maybe through your career or life, and it stick to your mind every day.
Yeah, from my parents for sure, working hard, and also enjoy what you are doing, but in particular, having respect for the others. This was one of the main advice from my parent. And sometimes say, oh my God, why they say that? But I think because it's very difficult, follow this path. But I really thank them for this advice, because they I mean, they guide me in my, not only in my career, but also, yes, my life and my career at the end are very close, you know, because we spend a lot of time and we love our job. And so I think that it's very important to respect the other people, because at the end you are much more happy. No, and so these advice are for me fundamental, and were in the past, they will be in the future.
Wonderful. I don't know if you have any final words you would like to say for the community before we close.
Of course, invite all the members of the community to attend the next conference that will be in Edinburgh, hopefully in person, and the general chair together with Adam Stocks. And so, yes, enjoy our work and try to be more and more curious and try to do great stuff as we are doing. So I'm waiting for all of them.
Thanks so much, Parvat. I think that was very inspiring, and thank you for doing that.